Hello to everyone, my name is Sheila Venero. I'm a PhD student at the University of Campinas, and today I'm going to present to you my work called Automated Planning for Supporting Knowledge-Intensive Processes. It was a joint work with the Carnegie Mellon University. So let's start. But what are the knowledge-intensive processes? The knowledge-intensive processes are very unpredictable process which involves a lot of complex decision-making tasks, like for example, how to manage an emergency, or how to decide a treatment for a patient. These processes usually rely on highly qualified and experienced professionals called knowledge workers. They need to analyze and process large amounts of data in order to make complex decisions. They use their knowledge and experience and expertise to define which procedures apply in these cases. Let's see an example. Mary was diagnosed with lymphoma non-Hodgkin, and now she's receiving RICE chemotherapy. Today, she was supposed to receive the second cycle of RICE. However, something unexpected happened. She has fever and presents a severe case of nausea. So physician needs to stabilize her situation in order to her receive the treatment. Physician usually needs to evaluate several strategies to handle with medical conditions. Assuming for this specific case that we have the fever management and the nausea management. Each of these has a lot of activities which interact with each other and have several constraints. Like for example, maybe administer a drug for nausea could cause some effects in the fevers of the patient. Or maybe the drug effectiveness could not be the same because of the historic of the patient. So even for this simple case, the combination of these activities between the tactics is very challenging. So how we could support knowledge workers to deal with this unexpected situation and help them to make decisions? How could we increase the level of automation and provide enough reactivity and flexibility to handle these knowledge-intensive processes? We propose to use automated planning techniques in order to create plans to help these knowledge workers. So we decide to embrace the decision making as a concept of the artificial intelligence. So we choose a specific case instance, analyze its current status and its interactive environment, observe a situation, and an agent takes some action in order to modify the environment and the case status of the case. So this action should be intent to achieve a goal. So the question should be, which actions do we should take with these circumstances in order to achieve an intended goal? For that, we propose to create continuously plans according to the ongoing circumstances. These plans should be revised, executed, and supervised continuously according to a knowledge base. And as soon as new information becomes available, this plan should be replanned at runtime. In order to develop our approach, we use the following concept: automated planning. Planning is the explicit and rational deliberation of action to be performed to achieve a goal. The automated planning studies the deliberation of this process computationally. The classic planning defines the planning problem as a state transition system, which is composed by a fourth tuple that have states, actions, events, and a state transition function that describes the behavior of the system. Actions are transitions controlled by the plan executor. On the other hand, events are aphorism transitions that correspond to the dynamic of the systems, and they cannot be controlled. Both actions and events show the evolution of the systems. There are a lot of planning algorithms to solve these planning problems. We decide to use the Markov Decision Process because it allows us to make decisions under uncertainty. Basically, an MVP treats planning as an optimization problem in which the agent chooses an action based on the observing state and receives a reward for this action, maximizing the probability to achieve the goal. In order to solve this MVP model, we use the probabilistic model checker PRISM. PRISM uses a simple state-based language which its basic components are the models. Models comprises variables and commands. The variables represent the state of the models, and the commands represent the behavior of the model. Costs and rewards are also expressed by PRISM. Cost and reward represent the certain costs associated to some transition of the model. So in order to define the process modeling as a planning problem, we need to formulate the planning model. So for that, we use the MetaKeep meta model, which is a former work developed by us. And this meta model allows us the definition of knowledge-intensive processes. It uses an artifact-centric paradigm to express a case model, context, and environment. It supports data-centric process management, and it allowed the explicit integration of data, knowledge, activities, and resources. MetaKeep comprises 4 major packages: the case package, which has domain artifacts, data objects that contains the valuables of the current state of the case instance. The knowledge package, which has which basically represent the procedures, the guidelines used in the business process, and also the control flow package that define activities, data-driven activities. All these packages allow us to the definition to the representation of a decision-making process. Like the domain artifacts allow us to represent the current state of a case instance. The knowledge and control flow package allow to represent actions, preconditions, and effects, which will give us which will provide us the evolution of the system. And all of these, and besides, we have the decision alternative, which could be also stored at the meta model, MetaKeep. With this element, we could define a planning problem, which basically we define it as an observable situation, which are the current values of the attribute in the case artifacts, the goal state, which are the desired output of these attributes, and the relevant planning operator, which represent the available action of relevant tactics according to the observed situation. The planning operator are instantiated by actions inside the tactics. An action is an executable activity which can modify the state of the case instance. An action has preconditions to restrict their combination, has effects that follow a probability distribution. Also, we could model the cost of an action that could be represent a monetary cost, time, risk, or something that we want to minimize or maximize. With this, we can generate a plan. For that, we use the Markov Decision Processes, and which allow us to generate alternative plans according to the knowledge worker preference. The figure shows an example of a generate plan, which is a state graph that represents the process model. The circle are the states. The solid lines represent the suggested activity, the suggested action to apply in these states, and the dotted lines represent the possible outcome of each after applying this activity. So now that we defined our planning model, we could model using Prism. So as we could see, as was presented before, Prism have models, so we need to have variables and commands. The variables are the attributes of the observable situation and the goal state. The commands are the available actions from the selected tactics. The rewards are the cost of performing these actions. The property file represents the goal and the plan criteria. That's something that we want to maximize or minimize. That could be the cost of time. After solving this MVP model, Prism gives us an optimal adversary, which for us represents the strategic plan or the process model. This is the algorithm for automatically generate the MVP Prism model. So basically, we need an input, the observable situation, the goal state, the set of tactics from the knowledge base, and we also add percentage that will allow us to select relevant tactics. The percentage of satisfied preconditions, which is basically for evaluate if the current state of the case instance work as a precondition to apply the tactic. And also we need to evaluate that if the goal from the tactic is related to our goal. So this percentage will allow us to select relevant tactics to show to the knowledge worker. After that, we present this list of relevant tactics, and the knowledge workers will use their experience and knowledge and again select the relevant tactics to do the MVP model. After that, we check the availability of the activities, create the planning operator, create the commands, create rewards, and finally create the MVP model on Prism. In order to test our approach, we developed an MVP model from the past scenario. So we had the Mary that his current status that's receiving chemotherapy, and her current status has fever and nausea. So this is represented as the observable situation and a goal state. So basically, the observable situation is that she has 38 degrees Celsius degrees of fever, and the level of nausea is 4. So we can see that's how we model in Prism. And the goal state would be stop the fever and control the nausea. So the goal state would be that the temperature should be between the values, the 36.5 Celsius degree and the 37.2 Celsius degree, and the nausea should be 0. Prism allows us to define the goal function as an utility function. So basically, we could express some preference along all the plan for achieving the goal. So we want to achieve a goal, but also we want to minimize the time for achieving it, or we want to minimize the cost for achieving it. Or for example, medical treatment could be to minimize risks or maximize the life expectancy of the patients. We model just time and cost. So imagine that the selected tactics were the fever management and the nausea management. Now we need to model each activity of these tactics. So we model these activities according to the probability to respond to treatment. So for example, there is a 60% of successfully respond to treatment, a partial 30% of the patient partly respond to treatment, and 10% of not responded to the treatment at all. So each activity of inside tactics should be modeled in this way. As activities in present represent the action, this is basically how we model in present. We have the command labeled with an action, the precondition to apply this action, and the updates, which are basically the probable outcomes. So the effects over a variable in the state model and the probability to achieve this. So this is how we model on present. And finally, with that, we have an MDP meta model on present. So we solve the problem, and it gives us a state graph which representing the optimal plan to achieve the goal while minimizing the cost in this specific case. So for example, we have the initial state that she has 38 weeks of fever and has 4 in the level of nausea. So it suggests that we should apply the activity B1, and we have 70% of chances that we reach that we control the nausea, and then we can control the fever applying the activity 1. And there are 6% chances to achieve the goal state. This is just a small fragment of the state graph. And as we could see, this is the alternative plan for optimizing the cost. We could also optimize the time or the life expectancy, as I said before. So in that way, we could give out to the knowledge worker different alternatives to choose for treat this unexpected situation. So as the concluded remark, we could say that we show how automated planning technique could be used to model knowledge-intensive processes at run. We described how to synthesize a planning model from an artifact-oriented case model, define it according to the meta model. We investigate how Markov decision process can be modeled using prints to generate plans. And finally, we want to, future will involve developing a full infrastructure for managing knowledge-intensive processes. So we will add a planner capable to interact with knowledge workers, and also want to improve the presentation of our plans in order to make them more understandable to people. So that's it. Thank you very much, and see you next time.